And there we go. All right, so see who we got. I got a pretty good group. Okay, so today we'll just talk about EMS, and I'll go on until you guys get bored or we've gone through enough. I will switch my camera over and go to the whiteboard here. And apply that. All right. Looks like a good share. Okay, so what is EMS? Everybody here has a pretty good indication what EMS is. Energy management system. It does control our energy needs for sure, but what we use it for the most part, is controlling our compressors, our circuits, keeping everything cold. And then the energy part gets into floating suction and floating discharge, head pressures. Floating will save a lot of energy. There's formulas to calculate that. We're not going to get into that, but basically what that does is the closer you can get your suction pressure to your discharge pressure, the more money you will save, period. Your compression ratios change. So that's where our energy savings comes in. Of course, they control the lights in the stores, the heat, the air conditioning, all that good stuff. And it saves energy there by setting back temperatures at night. It will make sure your lights, a very important thing, very important, actually, huge energy savings is it will, in certain instances, it will track the outdoor light outside. And especially, as the seasons change, we need lights to come on earlier in the evening. So we've got to set them till, the winter time, we've got to set these things to come on at 4:30 in the afternoon because it's starting to get dark. But we can't just do that, set it at 4:30 and be happy about it, because in the summertime, we don't need them till 8:30. So we don't want the lights on at 4:30. So it will track the light level outside. Newer systems, or any E2 for the most part, you can tell it what your zip code is, basically, and it knows when sunset is and sunrise, and it will adjust. So you can use, instead of a light level sensor, say your light level sensor goes bad, you can use the that part of it. I recommend it because the light level sensors can go bad, and since we're not a vendor, the vendors, they loved it. When we had a light level sensor, well, it's bad. You get to charge somebody to replace it. But we don't really need it. We have computers that are smart enough to know when it's getting dark in whatever part of the country you're in, whatever latitude you're in. So there's that. I think a lot of people struggle. They look at the computer and they're overwhelmed by it. It seems like it's such a big system. But you got to think of it like a robot. Okay? It is a robot. You guys are, I've said it before on here, you guys are robot technicians when you work on these EMS systems. It has like a robot. It's got a computer in it, and that computer makes things turn on and off or move whatever it senses with a sensor. So we're doing the same thing. We make fans ramp up and down. We turn compressors on and off based on a signal it gets in. And the robot is the board is like the hands and the arms and the legs of a robot you see walking around. A robot walking around takes data from sensors it's got, balance sensors, whatever else, any other sensors on all the joints, and it knows where everything's at, and it can maneuver around and do all kinds of fun things. But I think ours are way cooler, even though they don't actually walk. They do a much more important job. So you think of it as a robot, and I think it might be a little easier for you. So thinking of it as a robot, the actual controller is obviously the brain, right? That's where all the programming's at. And yeah, I know that there's case controllers and all that other fun stuff that has programs in it, but we would call those smart legs, I guess, or smart feet, smart arms. It still reports to the brain, the robot brain. So you look at the whiteboard, I drew a basic layout of a controller that looks like a robot. And you'll notice that, I'll go up to the board in a second, but you'll notice that the way it's drawn is actually the way you've got to wire those boards. It's called a daisy chain. We go over to the whiteboard and I'll continue on from there. Hang on a second. All right, make sure this thing's working. All right, so yeah, you'll notice it's just a picture of a robot here, but it is actually what we have. We'll call that the E2 controller there. That's the easiest one for everybody to work on, including me. I'll be sad to see them go. But again, I said that about Comtrol way back in the 80s, that I'd be sad to see them go, but at this point, God, they can't go soon enough. So you've got a robot brain, you've got a board, another board. This board's the hand, this board's a leg, this board's a leg, and that board's a hand. And you'll notice that the drawing has them wired up in a certain way. It's important that it's wired that way. The reason is because the communications that it uses, it's basically a voltage pulse. And you can't have, the voltage pulse has to go through the entire chain evenly. It can't be taking shortcuts, because then the pulse won't come out right and you'll end up having failures. It would probably work for a while, and I've seen them work forever, but it's just not the right way to do it, and it's just destined to fail. So if you look at it like we would show it like this, let's just say that we would put the boards like this. say those boards are all in a rack panel, and that would be wired in a daisy chain. Like that. Okay. So whenever you're checking the daisy chain, you know that it's all tied together. Each board and the controller is like 2 to 5 volts DC. And that's it pulses. And that's the pulsing is actually language that the controller can read. Same thing if you've got a case controller. It can read it too. And in these dumb controllers or the boards, they just do what they're told to do by the controller. So the boards can read it too, but they're not a smart board. It just does what it's told by the main controller. And it's all uses the 2 to 5 volts DC. You can read that on your meter. Does that mean you can tell if you've got a bad board by checking it right here? If you think that board's bad? Not really. Even if this board is unplugged, the 24 volts is unplugged, you'll still read 2 to 5 volts DC here because you're picking it up from this one and this one and this one and this one. So keep that in mind when you're trying to troubleshoot a bad board. You're going to want to always unplug it, take it out of the circuit and test it without it plugged into the comm loop. And it unplugged, this board should put out 2 to 5 volts DC. If it has 2 to 5 volts DC, it doesn't necessarily mean it's good though. I've seen bad boards still put out a DC voltage. It's just the comm chip is messed up or something's messed up in it. The first and last board have to be terminated. What does that mean? Well, at the end of the daisy chain, both ends, it has to be terminated. So this board here in this instance would be terminated. The very end board. Well, this controller is also a board. So in this instance, this would be terminated. And if you look at the board carefully by the comm loop, you'll see like some jumpers, some have dip switches. The CPCs usually have the dip switch. You just move the dip switches. It tells you how to do it on the board. So if you're having comm problems and you find that maybe a long time ago, this one used to have a board out here on a condenser and that's gone now, and they've removed that board. Well, it used to be this one would have been terminated, and if they removed it and didn't terminate this one, you could run into problems. So that's always something to check. Make sure it's terminated. There's a lot of people, including myself, that used to always think you had to, let's just say, I think I went over this a while back, but let's just say there was a board at the condenser. This is a good one. It's always on the, it's going to always be on the ones with the condenser you have this problem. Let's say this board goes up to the condenser, or this line, and this was terminated. But you've added some systems onto this controller and you want to put another board in, but it's down here. Well, technically, to make the daisy chain, if you don't know this little secret, you would run another line back from the condenser board to the board you want, and that would work fine. That would work perfectly fine. But remember, I told you the controller was a board. So you could put the board down in the panel and loop it in right there. Perfectly acceptable. Unterminate that, terminate this. Perfectly operational system right there. It worked perfect. Any questions so far?
I'm sorry, I'm a rookie, but when you say terminate, you mean isolate it?
No. Well, I guess yes and no. Terminated is it's just the saying that they've come up with in the industry to saying that's the terminus. And there's dip switches, or with the CPC boards, it's got jumpers that you would move. Let me see if I have a CPC board handy. I'll show you on the camera.
Danfoss has a dip switch for it.
Yeah, there's dip switches. There's different things.
So by changing the dip switch, you're just determining that that's going to that.
End of the loop, yeah.
Okay.
When we had new equipment get installed in the middle of the loop before, and someone had it probably came with the termination on. So it, if I remember correctly, it knocked out everything else on that loop.
Okay.
Everything after that board. Yeah, it's saying end of the line.
Got it.
I don't have a board. But there's going to be something there to terminate it. And basically I think what it does is it changes the resistance on some portion of this board and letting the signal know that there's nothing coming back the other way. It's just going one direction. You're not going to expect anything coming through. It's the best way I could describe it, but in all honesty, I don't even really know what it does to the board. But it's important.
What it's doing. It just determines what it's doing.
What's that?
It just determines what it's doing. You're just telling it, do this. Loop ends right here or whatever.
Yeah, I'm not sure what it does in the board, but the controller can't tell, and you can't see in the controller if something's terminated. It just does something to the electronics to let it know that it's terminated. And like I said before, I've run across systems that have been running for 5 years, boards aren't terminated, and it hasn't had a problem. So I'm just repeating what I've been told over the years, and I've seen it done, and we don't have problems. I have seen systems that's not terminated, and we do have problems. Or if you have a board in the middle and it's terminated, it'll cause problems as well.
Okay, so you're saying that you terminate the first and the last board?
The first and the last board, correct. On the daisy chain. Remember, it's got to be one line going through.
Gotcha.
So,
okay.
So if this board is the first, and that's the last, or vice versa. I guess it doesn't matter. The end of the line is what you got to look at it like. The end of the line. And again, if the controller is the end of the line, then the controller has the little pins, I guess, for lack of a better word.
I think, Mark, isn't in most of our cases the termination starts at the controller and will end at the last board? I don't think we typically terminate the first board on ours, do we?
Well, yeah, I think you missed the part. So I think you missed the part. So I first had it drawn like this, where this controller was terminated. And then you got one at the condenser.
Okay.
And I said, hey, if you ever need to add a board onto here, you don't need to run a line from the condenser board down.
Okay.
You are allowed to unterminate the controller.
That's my fault.
Put a board in and connect it. You're also allowed to, let's just say, you're not near the controller, or let's just say that you just want to put another board in here. You could squeeze one in right here and then move. You can't just run a third line like there. That's a star formation. So another good way to look at it, if you have 3 wires going into one there's a problem. It's not correct. That's a star configuration. In this instance, you would just move this line over to this board to continue, keep the single line going, the daisy chain. Don't interrupt it. I don't know what it is that causes the problem, but something in there messes up the way the voltage flows. That's a little better, I think. Okay, everybody with me so far? So that's the basics of the boards. It's literally a robot. It controls stuff that's moving. It controls movement. It controls compressors coming on, fans ramping up, contactors, anything that you want to control in a store, you can. Anti-sweats, you can control. As long as you know what you want to do with it, you can, anything your heart desires. For me, simpler is better, but when it comes to spending electricity in the stores, they want to save electricity, so it can get kind of complicated, especially when you start getting into the demand defrost. I'm so glad we don't do that here. We did that at Kroger, and it's just a nightmare. Everybody got that? It controls fans. You need more fans. The controller sees it. How does it see it? From an input. It sees the input of the pressure. The pressure's going up and up. You've told the controller you want to keep it at a certain pressure. So in the controller, it knows if the pressure is higher, more fans up here. As the pressure comes down, the controller has been told that, hey, once it gets down here, turn off fans. So it starts to stage them off. It's a sequencer. It's a defrost clock. It's a compressor sequencer. It's everything we've always wanted in this trade, and some things we don't. But any questions on that? The basics there of how it's wired. 2 to 5 volts, remember that. Most boards work on DC volts. There is some I've seen that have AC volts, 24, but most everything we have powers up with a 24 volt power supply with a center tap on any particular board that calls for it. All of the newer CPC multiplex boards with the relays and the AIs, that's just a 24 volt. It's just a 24 volt AC circuit. I think I said DC. AC. circuit for these 24 volts. The center tap is just the center tap off a transformer. I'll get into that right now. Let's show you how that works. Transformer, let's call this 208. 208. Iron bar. $24. Okay. 24 volts. AC is what's going to power these guys up. Some of them have a center tap on the transformer. That's literally what it says it is. It's just tapped right into the center of that winding. A line coming out. That's going to be 12 volts. It's like a neutral on your house panel. It's a center tap. Now, it's only 12 volts between the edges. Okay, so on the two outside will be 24. Line 1 to the middle, 12 volts. Line 2 to the middle, 12 volts. All the control boards, I think for the most part, have a center tap that I can think of. I don't think there is any controls that don't, right? Am I wrong about that? I think they all have it.
And what is that 12 volts for?
I believe it's in control. It's to power up. It makes it power up for the actual sensors and the transducers. That's a good question. I don't know why they have to have it. I know that older CPC boards and the any AI board for CPC, and I believe the single RO boards as well. But it's all in the book. Which boards need it. It's important to follow that rule.
I had one store that I think I was getting like 10 volts from the control to a switching relay, and it almost wasn't enough to do the relay unless I tap it. Then it would turn on the compressors.
And you had 10 volts on the center tap?
I had 10 volts on the coil of the relay, but I wasn't able to find the board to locate it. But when the board would call it on, I would just touch the relay and it'd kick on, but there'd be 10 volts there, and you would have to like hit it to get it to turn over.
Now I'm confused. 10 volts on the electronics on the board, or on the Phoenix connector?
So I wasn't able to check the board, but according to the wiring diagram, the board sent power to the coil of my switching relay that would send the control voltage to the compressor on the other side. So I would have 10 volts at the relay, which I would assume would have been enough to hit that switching relay, but I would have to tap it, just give it a little flick for it to actually pull the coil in to do what it needs to do.
Oh, okay. So not on the RO board, right? This is on something else?
Right.
Okay. Yeah, if you
But the
have
power
too low,
came from the board.
if you have too low of a voltage, then for sure your coil of any relay is not going to pull in. But I believe that this. Go ahead.
So 10 is too low on a 12.
Oh yeah, 10 volts is what the like a controller operates on 10 volts AC. It's possible that they had the wrong transformer. It had a control 10 volt.
Oh, okay.
But you'll see that all controls have 12 volt center taps, and some CPC have center taps as well. Now, when we have a bad transformer, we don't have to use the exact same one. As long as the VA is correct, and any multi-branch transformer will work. And so that's what I've been buying because, you know, you're never going to find a control transformer unless they're old ones that we have. So I have bought the regular transformers that just have the bunches of wires coming in and bunches of wires coming out. So you would hook up the high voltage side like you normally would, the 208, and be careful on transformers, guys. This is important. And I don't know if it gets said enough. When you get a transformer, you're going to notice that it's got a 240 or a 208. We use 208 volt in all of our stores because it's 3-phase panels. There's very few exceptions. There is exceptions, like some of them older stores with those stinger legs will have 240. Check it and make sure you hook up to the 208, not the 240. I believe that's the orange leg. So keep that in mind. If you hook it up to the 240 side, your voltage coming out is going to be too low. Won't be enough voltage over here. Because the 240 is going to be more windings. And then over here. So if you hook up 208 to the 240 side, it's going to be a weaker field through the iron bars. Meaning you're going to have less voltage on the output. So that's one thing to keep in mind. All right. And then a multi-tap will also have the 120. Same thing. It's the basic typical diagram right there. That's pretty much how they work. So keep that in mind. So you can use a they call it a multi-tap transformer and get the right voltage to power up your boards. Just keep in mind that most of these, I think, are only like 48 VA. I think they might power up 3 boards. But you know, again, the book will tell you how many boards, because each board's different. Some boards take more power than others. A multi-flex board with both the AIs and ROs takes way more power than a analog input board. So keep in mind, always fall back to the book if you have any questions. And all the books will tell you. If you guys don't have the E2 books, I can send that to you. It's obviously not a book, it's a PDF. It's hard to find the information in there sometimes, but it's in there. Like how many boards, you know, each board, it'll tell you what each board needs. Let's say multiplex 168, you know, needs 10 or 15 VA. 180, 88 plus 10 VA. You got to add all that up and see how many VA transformer. Or you might need more than one transformer if you got enough boards. So, you know, you might get away with one big 75 VA transformer or the little 48 VAs. I haven't found a multi-branch yet that I'm sure they're out there that are more than 48 VA, but that's pretty typical. We'll power up most of our controls in our E2 stores. So when you wire it up, there's going to be a 0 volt. I think that's how they are. 0, 10, 12, 24, and 48.
Mark, the E2 ones just do their 80 VA and they have the center tap for you all built in and shit.
Which ones?
The E2 ones?
Yeah, the E2 ones?
Yeah, those are the best ones
you can get if you could find one.
Yeah, you can get them from you can order them for you. I think we have a whole box in the shop.
What's that?
We have a whole box at the shop, remember?
Well, we have the multi-tap ones, a whole box of those.
What's the difference between that and these?
Huh?
What's the difference between that and these? Why would we need 48 volts?
I just think that's on there. You just tape it.
The one
You cap it.
you're talking
I
about
think
like
they
the
have-
ones for the old Comtrol transformers? And the old like Comtrol ones?
That are all soldered.
Yeah.
That would be like this guy here. I'm talking
Oh.
about you could just, if you can't, you're in a pinch and you need a transformer,
Oh.
I'm just drawing a multi-branch.
I've had a hard time getting those from United. Like with the CBC ones, the only ones I've ever been able to find that even do 12 volts.
The ones we have at the shop do.
Yeah, like
The
I've tried getting something with a center tap before from United, and they just look at me like I'm crazy.
Yeah, they used to sell them.
I don't know if they do anymore. They just give you the one that does like it has the multi taps, but it's like 24, rear right, maybe 48, but usually they skip over the 12 or something.
Yeah, that's what I'm saying. If you get the ones with all the wires coming out, I think they're made by RIB. And I've been picking up 10 at a time from United, or not United, from Granger's.
Oh, okay.
And so what I'm saying here, though, is you would cap anything that you don't need. So that I think they have a 10, you cap that, and all you need is these 3 wires. The 24 to 0 is your 24. The 12 is your center tap. It's the same thing here. It's center tapped in here. So on this one, that would be your 0. Just put 0 here, 12 and 24. That's how these guys are wired inside there. But it's the same thing. If you run into a pinch, you need a transformer. There's a box of them in the shop, brand new. They'll work. And I used to get those all the time from United because they're getting better at having better transformers. But there was a period there where they didn't have anything. You were screwed. So I guess the point here is just don't forget you have a center tap on these boards, a lot of them. And it has to be there. It has to be used. Again, the multiplex boards, I've seen also on the multiplex boards, the center prong is grounded, like to a screw. I don't know if that's important or not. I've always seen it. I just always left it like that. I'm sure it's important, but that is what it is. So yeah, if you do end up with one of these with a bunch of wires coming out, you'll use the 24, the 12, and the 0. 24, 12, and 0. Same thing.
Hey, Mark, just I looked it up. The VA for a multiplex 168 is 15. So you can put 3 of those boards on that transformer.
Yeah, I guessed that 15. Pretty good guess.
Well, I don't remember that. We'll watch the video and double check.
It's being recorded, so. I said 15 for a 168 and 10 for an 88 plus.
10 for an 88 plus. All right, let's look at the manual here.
And Brandon's looking at the same book I told you guys all you should have. You should have that book.
Actually, it says the 88's 15 as well. So 88 AO, 168. The only thing that shows the 6 VA is a multiplex 16, which I guess is just the AI. So the AI board's only 6 VA.
Only 6?
Yeah, everything else they say is 15.
Yeah, so you have to add all that up, gentlemen. So remember, if you've got one transformer powering up 1, 2, 3, 4, 5 boards, you need one big transformer or 2 smaller ones. You don't want to overload it, because then you're going to be right back in the same position you were in. So 48 VA is pretty typical. Like Brandon was saying, the 80 VA is what you see a lot of on that has a lot of boards. I think they have an 80, a 50. And I think those are the two main ones you'll see. But the ones at the supply house, I don't know why. They're 48 and 75 VA usually. But yeah, you could put 3 boards on one of those little transformers. They're easy to hook up, and the wires are long, and you don't have to solder them. Makes it nice. A lot of these transformers on Comtrol you're going to find are soldered in. Those are always fun. So that kind of talks about the power on them. Let's talk about the different boards, and then we'll talk about the different sensors. So remember, to go over kind of what we did, EMS is basically a robot. That's the brain. And these are the appendages, all of our boards. It takes inputs, and whatever you've programmed it to do, it does an output. So it's always reading an input and doing something with that information. The inputs are your analogs and digitals. We'll go over those in a second. Outputs are analog or digital when it comes to most of them. A digital output is a relay output, RO. So everything's analog or digital. I guess before we go over what the boards are, let's talk about what is, why do we call it analog and digital? I'm sure that's a question that some of you have pondered. All right, who's texting me?
Mark, what's the why is there a person in here that says mod unverified?
That's our YouTube moderator.
Oh, when you post this to YouTube, that's what it does, or what?
It's live streaming on YouTube right now. Say hi to everybody.
Hi, everybody.
Our moderator says we have 0 people watching, so we're not doing so great.
Need to get some women, some bikinis on here. Maybe we'll get some viewer numbers up.
We need to step it up with the models.
I'm retired.
Okay, so what's an analog and what's a digital? Everything we work on here is either analog or digital. Everything. Analog. Digital. Analog basically means it's a spread of something. It's a zone. It measures more than just on or off. We'll start with digital. What's digital? On or off? That's it. Everybody knows what digital is now. On or off. How computers work through computer language with at the speed of light, things going on, off, on, off, on, off at certain patterns, and it creates code and makes the world go round. I was looking for my pen everywhere. It was in my pocket. On or off? Those work great to a certain point, right? On in digital output, compressor running, fan running, anything else running. Off, those things are off. Digital input is a closure. Let's go digital out, digital in. Digital in is the same. On, off. Digital in means information coming in to the controller is either, why are none of my pens working? Somebody take all my ink. Let's just do like a switch. That switch is open. That would register as off. There's very little voltage in there. You're gonna read voltage in there, but what it's really reading is the resistance in there, for lack of a better word. It's reading an open circuit, just like as you take your meter and you check across that switch, your meter knows it's open. This does too. It sees it as off. Tells the computer brain that switch is open. That's all it's doing. Digital in. Close it. Now it's on. Computer knows it's on. That's a digital in. Very simple. Digital out, same thing. That's just going out. Turns on something. So on would be a closed relay. Turns on compressor. Fan. Heater. Obviously, we wouldn't run a compressor through there because the amps are too high. So this would all be on a contactor, as we all know. So digital out. So let's just say the digital in, let's just say it's a door switch, okay? It's open, meaning it's off, which will turn the fan off using the computer brain in a board. So let's call this the AI-DI board, and this is the RO. Door switch is open, tells this board, hey, I'm open, tells the brain, hey, you're open, sends a signal out through here to the RO, you better open, because we need to shut this fan off. Okay, that's it. That's all it is. Digital in, digital out. Closures, on, off, on, off. Door switch closes. AI sees it, tells the computer, I'm closed. Do whatever you do with that. Computer says, I need to turn the fan back on. Sends a signal out to the RO board, turns the fan on. Okay, that's a very simple task on walk-in freezers, right? So if you're ever troubleshooting a walk-in freezer, that's all it is. It's that simple. It's nothing more than that. Now, obviously, it's not just the door switch that turns that fan on and off, and that's where the programming comes in. In the program, you'll tell it, also in defrost, shut the fan off. So the door switch can shut the fan off here, and defrost. It needs no other inputs other than a time. So a digital input could also be a timer. Or, defrost. Time. That's also a digital input. A lighting schedule. It's a digital input. What other kind of digital inputs are there? Termination. Digital input. What else we got? There's probably a whole bunch I'm missing, but anything that is a closure, on or off. On or off, digital input. Digital outs, on or off, relay. I don't know if there's any other digital outs other than just a relay output. It's just on or off. Analog. I don't know how to spell. That's a little different. Analog out, analog in. Same thing, only this has a spread that could go in infinity, basically, anywhere in between. You can set it up whatever you want. Analog out. Most of the time we use 0 to 10. We'll just call this a condenser. 0 to 10 and anywhere in between, including decimal points, but we'll forget that now. So anywhere 0, 1, 2, 3, 4, 5, all the way to 10. It's like an output, but it can get there. It doesn't go open and close. It's actually a number. Analog in's the same thing. This is output. This is input. Analog in is, let's call it a transducer. Most transducer, they're called a 0 to 5 volt. In reality, it's 0.5 to 4.5. You know why they do that? Anybody know why they do a 0.5 to 4.5 on a 0 to 5 volt sensor? Anybody?
Different levels of resistance.
No. Good guess. The answer is so you go ahead.
Because it goes on increments of 0.5. So 0.5
No.
is technically 0.
Good guess, though. Anybody else want to guess? The reason it's 0.5 to 4.5 is so that you could tell if it's failed. If you had 0 to 5 and somebody unplugged it, you would just have 0 volts. It would just say 0. You wouldn't be able to know. If it failed and had 0 volts, you would never know. The only reason you see these things that's failed is because it's 0.5 to 4.5. If it sees a 0, it knows it's failed. That's the only reason. The 4.5, same thing, I guess, but it's mainly for the 0.5. It has to know if it's failed. It has to know if it's unplugged. It has to know if it's lost its power supply. It's got to know if it's failed. That's the way it knows. So when you see these shorted sensors or whatnot, that's why it knows. So that's the reason it knows. Analog out. So this is voltage in, basically. Analog ins, we're going to call everything voltage in and voltage out because we don't have any of the milliamp systems. That's other brands. They do have milliamp, 4 to 20 milliamp. They're kind of nice because they only need 2 wires, but we don't have them, so we're not even going to discuss them. Analog out is a voltage output. Mainly, we could do 0 to 10 volts or anywhere in between. That's kind of our range. Because it's working on a 12-volt system, we don't really have anything more than that. That's kind of all we have, but that's all you really need. That's got a pretty good spread, so you can really control something. As we know, you can control something really well, like just say, for instance, the analog ins for the liquid levels, they're 1 to 2 volts. But it can go from 0 to 100 in that 1 to 2 volts because it's got decimal points. So it's an infinite range that we have. You can control a condenser drive on 1 to 2 volts because in between the 1 to 2 volts, you've got 1.1, 1.2, 1.3, 1.4. And you could tell it, hey, it's a 1 to 2 volt, and it'll do its own calculations and it'll run fine, just like it's a 0 to 10. So analog in is analog. It's like your analog gauges. It's anywhere between from 0 to 10 here and from 0 to 5 there on the inputs. We don't have much that's more than 5 volts on inputs, except for like light level sensors, humidity sensors. Those are going to be higher inputs. Old transducers, be careful. They're different voltages. Even though the outputs were the same, the voltage powering those were 12 volts, and you'll burn up. And honest to God, I don't know why they burn out so quickly. It's literally 12 volts DC is nothing. But if you plug that into a 5 volt Eclipse transducer, it's instantly burned out. Instantly. So I don't know why we have something that weak in our systems, but there we have it. So you plug 12 volts into an Eclipse transducer, poof, it's gone. And you don't even get to see the smoke coming out of it. Just instantly gone. All right. Any questions or comments here? My dog has a comment. Let me in. Get in here. And my dog was super sick, but that was on Monday, and over the weekend, but she has come through. I think she had COVID. Okay, so I guess we could get into a little bit of the. You guys want to get into a little bit of the wiring of the transducers or even the sensors? The analog inputs are not just a transducer, but that's a voltage input. A sensor is like a resistance input. The boards are always putting out voltage, just like your voltmeter. When you go to ohm something out like a compressor, and you can see the resistance in it, these are doing the same thing. Your voltmeter, if you were to test it with another meter when it's on ohms, it's actually putting out voltage. And it knows by how much voltage comes back, the resistance that's in the device that you're testing. So that's also so let's see what we can come up with. Analog ins, transducers, sensors. What other analog inputs do we have? Light level. RH. I'm sure there's a whole bunch more I'm missing, but anything that the computer needs to know an analog signal between 0 to a certain number, it needs to know an exactly precise number. That's an analog in. Digital in is just either on or off. This is a precise number, analog in. Analog out. That's literally voltage coming out of the board. All right. Hope she'll live. All right. Analog out. Let's just take, for instance, a condenser drive. We program it 0 to 10 volts for the most part, 0 being off, no speed, 10 being 100%. So if you want to know, you want to test your analog outputs ever, the best way I have found is set the thing to 100%. Make sure you got 10 volts coming out. Set it to 50%. See if you got 5 volts coming out. If you've got that, you're pretty well assured that it's pretty well calibrated there. Analog outs are any kind of drive. Let's see what analog outs are. VFDs. Digital compressors. It's funny, they're called digital compressors and they use an analog out, but digital compressor is kind of dumb. But it is because it's an on or off, like an unloader. What else we have analog outs? Anti-sweats. Actually, that would be, I guess that would be a analog. No, those are like a digital output. Never mind. Anti-sweats are a different thing. That's over there. That's a digital out. A different kind of digital out. So let's put that over here. Anti-sweats. Digital compressors, VFDs. What else do we got? I think that's all we use them for. If it was an actual robot that's walking around, you would use an analog out to move the leg forward. Let's just say you tell it, hey, I want to walk forward. It gets an input, it gets a digital in saying, go ahead and walk forward. Well, the leg will move forward using an analog out. It'll then get like an analog in saying the balance is good, or keep the balance or whatever. And then another digital in will tell it when the leg's extended and it knows it's good. And then the other leg will move. It's the same thing. It's literally a robot. It uses all these same things we use. Analog out. Yeah, for the life of me, I don't know why I can't think of another analog out we use, but I'm sure they're out there. How we doing on time? We're not doing good on time. All right. Everybody got all this? Because I do get a lot of calls and for tech support on this kind of stuff here. And this is the main stuff. Once you know all this, you can't program one of these unless you know all this stuff. This is first. This comes first. You got to know all this. Once you've got all this down, then you can start learning how to program, because again, this is more difficult. All this, all the boards, how it works is more difficult than program, because all the program is you know what you want it to do and you basically type in, this is what I want you to do. It's simple. This is the tough part. This is the whole stuff that you guys are working on all the time, every day. All right. I think I'll talk about how we wire up analog ins, because you all know how to wire up an RO. Remember, digital outs, compressors fail on, so that's always on the normally closed. Defrosts fail off, always on the normally open. You guys, anybody not understand that? On a digital out, you're going to have 3. You're going to have a common, normally closed, normally open. Right? Compressors, always wire to those two. Normally closed and common. Defrost, heaters, always wired to normally open. And we do this, and I'm going to say that's almost always the rule, but we're going to call that always the rule right now, and I'll come back to where it's not always. But defrosts are always normally open, and we do that in case you lose power to these boards. It goes into what we call fail-safe, and it will fail compressors on, defrost off. We do not want these things failing into defrost. That's bad. What are the instances where a compressor does not always get wired common to normally closed? Every single protocol unit out there has half the compressors wired normally closed, half the compressors wired normally open. For a good reason. It doesn't have a switchback loop. It's not necessary. It's literally done so that if you lose the board, your RO board, only half the compressors come on. You don't want to freeze up your entire meat counter, and it happens quick. It's better to have it, alarm and give somebody time. It also won't ice up nearly as bad. You got a plus 20-degree coil system and it's running at minus 10 until you get there. Coils are going to be iced up bad. But if you got a plus 20-degree system and it fails and it runs at plus 25, well, you have a lot better chance of not having everything iced over solid. So that's where half of them, and every rack we make at the shop, it's the same way. Half wired normally closed, half wired normally open. It's a safety. Gives you some time. How is a transducer wired? Everybody knows what a digital in is. Let's take this off. We're going to go over a transducer, and then let me see what time it is. And we might have to stop, and we'll carry on. Yeah, it's almost 8 o'clock, guys. I'm going to go over basically how a transducer is wired, and it's not that difficult. Let's just put a board here. I'll do a control because I don't know why it's ingrained in my mind. You'll have on a control usually 4 of these. Let's just do half the board here. Board 1. You're going to have one of them that is plus 5, one of them that's plus 12 on the little guy, the little terminal. This is where you need to be very careful. Old controls, let's say we're going to be working on point number 1 here. You're going to have a common and a, oops. Point 1 is the common, and then you'll have 1, 2, 3, and 4. The common, you're going to almost always see many wires hooked to it because that's the common. The point is what is going to be the signal to your transducer. So let's draw it going out there. Let's draw an old transducer. This guy was an old 12 volt. You got the signal to 1, common to common, the 12 volts to 12 volts. This is what everybody's got. You got to be real careful about this because they're still out there. I see them every now and again. It's rare. Used to be real common back when the Eclipse became very popular. The Comtrol had that 12 volts transducer. All transducers that you buy today that we will use are going to be called an Eclipse transducer. They're going to be plus 5 volts supply. All of them. If you hook it up to 12 volts, you might as well just go down to your truck and grab another one because it's going to be broken. Another thing, do not put these into a deep vacuum while they're powered up. They just stop, they fry. So that's something to keep in mind. Whenever you put something into a vacuum, if it's got a transducer, disconnect it or valve it off or something. You don't want to put those in a vacuum. They'll take some vacuum, but deep vacuum, it will not hold it. It will fry it. If you ask me why, I don't know why that is, but I just know. Don't ask me why. Don't ask me how I know. I know. I've burnt out a few, not believing it myself, but it's true. It will always be to 5 volts, anything new. This will be the red. This will be the black. And that'll be the white. The signal. If you're testing this transducer, you'll test 5 volts to black, and you should have 5 volts. It's not necessary to ever really check the 5 volts to the signal unless you like doing math and you like punishing yourself. If you want to check and see how accurate it is, though, let's just say you've got a 0 to 200 transducer right here, 0 to 200. And you check between black and white, and you have 2.5 volts DC. What do you suppose your pressure should read? This should be an easy one because it's easy for me, and I'm not good at math. If you have 2.5 volts between the black and the white, that thing should be reading 100 PSI on your controller. If it's not, there's a problem. You'll need to calibrate it. Or the transducer could be bad too. But you normally calibrate it with your gauge, obviously. But if you don't have a gauge and you want to kind of know how it's working, or if you want to make sure it's working good, you can change the pressure. Your voltage right here will change, and it's analog between 0.5 to 4.5. So 0.5 is 0, 4.5 is 200. Everything in between is analog, analytically equal to whatever the pressure is. Does that make sense? I hope that made sense. Made sense in my head. All right, it's getting late. I don't want to keep everybody out. Uh-oh, Jeff's on call. Pavilions 2212, lost all AIs, lost AI, and 8 RO. All right, so I guess if you guys want to watch me do that, I'll do the spin first, and then I'll stay online, and I'll get onto the computer here, and can watch me check out. Hang on. Okay, let me finish up the Wednesday group, and I'll check. And I will share my screen and do it, run it, so you guys can see what I do when I'm checking this stuff. But is there any questions on this while I'm up here at the board? I can go over it. And next group, we'll just have a real quick refresher. I'll leave this up, and we'll start right here at this. And we'll move all the way into programming if you want. We'll cover it all. We barely scratched the surface here, guys. And I think I went a little too quick. I might have gone too quick. So think of any questions you might have with what I went over, and we'll start again. I don't know. Maybe it's cooled off enough. We can go back to every week. We'll keep 2 weeks for now, and then in 2 weeks we'll go over it again. Let me take a pee break here, and then I'll come back. We'll do the spin, and I've got to log on, unless Brandon or Nestor, you're logging into it now. Oh, looks like we lost Brandon.
Log into what? What are you logging into?
2212. Is that one of your stores?
Not mine. What city is that?
2212, Lost AI and 8RO.
Oh.
Jeff's on call. He probably just got the call, and I don't know how he knows exactly what it lost.
They can pound it, Mark. It's an AC. I'm not kidding. It's an AC. Nobody needs to run it.
I bought a drone, man. I think the thing's cool as shit. Anybody else got a drone?
I wish.
They're cheap now. Right now, the DJI just came out with one, $199, fully automatic. Like, your kids can use it. It's like bulletproof. It's like a little drone, and you just the fan blades are all covered and stuff. Really cool. Automated. You just basically tell it what to do, and it'll like do all this cool stuff. Called a DJI Neo. All right, I'm back. Let's see here.
Another somewhat nuisance call.
Probably.
They had the
Right.
shells reaching out almost outside of the case. They're saying it's running warm. I was like, well, grab the one in the back. It's like, this one's cold. I'm like, exactly, dude. It's in the case.
Oh my God. All right, so I think I'll sign out of our YouTube stream here. See you later, everybody out there in YouTube land. But you don't get to see the spin the wheel. That's only for the inside guys. The guys who know.